Okay, let's unpack this. We are diving into a realm that, uh, statistically speaking, should be pretty quiet by now. We're talking about the Atari 8-bit computer line, the 400s, the 800s, the XLs, the XEs.
Right.
These are machines whose internal architecture was, fundamentally cemented way back in 1979. They're over 4 decades old.
And
yet their ecosystem is just,
yeah.
it's vibrating with new life.
What's fascinating here is that we're not just witnessing a maintenance effort, like keeping an old car running.
Right, not just preservation.
No, not at all. We
Yeah.
are witnessing what we have to call a second maturity. Developers aren't just preserving old tech, they're actively fulfilling the technical promises of the original design team from, 1984.
And in some cases, pushing it way beyond what was even imaginable back then.
Far beyond. It's a blend of high-fidelity engineering and, frankly, some impossible software design.
So that's our mission today. We're going to look at the state of this ecosystem in late 2025. We're pulling from forum chatter, deep technical developer notes, contest results.
All the good stuff.
Exactly. And we're zeroing in on 2 main themes for you. First, the technical struggle to resurrect and complete the hardware that Atari itself never finished.
The lost peripherals.
Lost peripherals. And second, how this ingenious software is turning these 8-bit legends into fully modern networked machines, capable of things that, well, no one saw coming.
It's the ultimate expression of creative constraint, isn't it?
How so?
We're seeing a community of engineers who look at the limitations of the 6502, that blistering 1.79 megahertz speed.
Blistering.
And they don't see a barrier. They see the perfect challenge. And they are conquering it through sheer ingenuity and a deep, sometimes painful understanding of vintage silicon.
Okay, let's start with the physical machines themselves.
The hardware.
We're beginning with projects that are literally completing the work left undone when Atari Corp, under Jack Tramiel, decided to, pivot away from expensive peripherals.
Right.
And if there is one project that defines this idea of finishing Atari's homework, it has to be the 1090XL expansion system.
Oh, this is the stuff of retro legend. For context, after Atari released the 600XL and 800XL, they had this grand vision for endless expandability.
And the 1090XL was that device.
It was a massive expansion box canceled in the mid-'80s. Its whole purpose was to provide 5 parallel bus interface slots, PBI slots.
And these PBI slots were the real game changer, correct? They were like a direct highway to the machine's central bus.
Precisely. They were meant for serious high bandwidth upgrades. We're talking 80-column video.
Which was essential for any kind of, business use.
Absolutely. Word processing, spreadsheets, plus large memory expansions, and critically, Z80 CPM compatibility. The 1090XL was Atari trying to make the XL series a real competitor to the Apple II.
Capable of running a professional operating system.
Exactly. But when the project was shelved, all that technology just vanished.
Until now. Because developers are recreating the peripheral cards that would have gone inside this canceled box.
Right.
And the developer notes we have from Brian Reifsnyder on the 1090XL parallel serial card they're just fascinating.
Yeah. They're a deep technical rabbit hole. A pure lesson in physical engineering constraints.
What was the core problem he ran into?
The paradox is this. When you build the original schematic today, using modern, much faster chips, the design just fails. It doesn't work.
Why? How is faster hardware a problem for an older design?
Because the original 1980s era components, especially the old TTL chips, were inherently, they were slow.
Right.
They actually relied on their own sluggish nature, their slower transition times, to function as timing elements. The original schematic just assumed this built-in lag.
So when Reifsnyder used modern high-speed equivalents,
that critical lag was gone. The signals started overlapping or transitioning too quickly for the rest of the 6502 bus to even register them properly. The timing it completely failed.
So the modern board is ironically too good for the 1980s architecture.
It is. It's too fast, which means he had to invent a completely new engineering solution, what he called glue logic. He had to add new components specifically to artificially slow down and regulate the timing signals. He used a very specific pair of chips for this, 74LS123 and a 74F74.
And what do those do in simple terms?
They work together to create what he called a specialized variable Phi2 signal.
Okay, let's pause and translate that. What is the Phi2 signal, and why did he need to make it variable?
Phi 2 is the main system clock for the 6502 processor and the whole Atari bus. It dictates when the CPU reads and when it writes.
Like a metronome for the computer?
A very precise metronome. The timing needed to be regulated to ensure that the read cycle had a long high period, giving the system time to read the data, but a short high period on the write cycle. If you're off by nanoseconds, the entire system crashes.
So the glue logic, those two chips, is basically a traffic cop. It's managing the speed of these hyper-fast modern components to match the schedule the 1980s computer is expecting.
That is a perfect analogy. He's building a regulator right onto the card itself. And this challenge is why the project is already on its 5th board revision. It's not just soldering, it's troubleshooting scope readouts, finding bugs in programmable logic.
And I imagine the physical hardware hurdles go beyond just timing.
Oh, absolutely. Component sourcing is a nightmare.
Yeah.
Reif-Snyder notes that even when he gets the logic right, finding the parts is hard, the proper PBI connectors themselves, obsolete.
And what about the core chips?
The card needs a Riot chip. That's a complex peripheral chip for I/O and timers, and two 6551 ACIA chips.
And those 6551s handle the serial ports.
Yes, the asynchronous communications interface adapters, they handle the dual serial ports. These chips are not only expensive, but they're getting really hard to acquire reliably, so this whole resurrection is costly and incredibly complex.
And it gets better. On the software side, the original ROM code for this card was found.
It was.
But it was described, I think generously, as alpha-level code.
That's a big deal. It confirms that Atari canceled this thing long before it was ready for production. We're not just finishing the hardware, we're debugging 1980s firmware.
What was wrong with it?
For a start, the RCIO handler, that's the routine that's supposed to control the serial port, was never actually implemented.
So it did nothing.
It just returns a success code, but it doesn't actually do anything. And worse, Reif-Snyder found a bug in the code that could lead to a stack overflow.
Which crashes the machine.
Completely. The stack is where the computer temporarily stores return addresses. If it overflows, the machine just gets lost and dies. So he's doing critical stability fixes alongside the hardware design.
This all leads to the question of speed. The 6551 chips define the serial limits. The datasheet says 19,200 baud, which is okay for the 80s.
Decent, yeah.
But there's this tantalizing discussion about getting it to 115.2K baud.
That massive jump, nearly 6 times faster, is crucial for modern utility, especially for networking. The discussion revolves around the W65C51N chips datasheet. It implies that if you set the baud rate selector pins all to 0, the chip might default to its max speed of a 115.2K.
So is that a hardware change or a software one?
That's the million-dollar question. Does it need an external clock signal fed into one of its pins? That would mean more hardware mods. Or is it just a matter of grounding the right pins, which would make it nothing but a programming change in the firmware?
And if they can achieve that, the card becomes dramatically more useful for the modern community.
Instantly.
So what's the grand technical payoff for getting this specific card working perfectly?
The ultimate goal is running CPM from other Atari machines. Using something called CPM IO byte redirection, you could take a standard Atari 800 or a 65XE and through the 1090XL redirect its I/O to a serial port on the expansion unit.
So the 1090XL becomes a dedicated CPM processor and the host Atari just acts as a terminal.
Exactly. It's fulfilling the promise of a complete 8-bit business system that was canceled 4 decades ago.
Okay, so moving from resurrecting internal expansion to connecting these machines to the modern world.
Right.
The video and audio landscape has been completely transformed. If you own a classic Atari 8-bit today, the solution for modern displays is really becoming the Sophia 3 digital video board.
The Sophia 3 by Simius, yeah. It represents a complete break from the past. For decades, we were stuck with blurry composite video or, maybe S-video if you were lucky.
And the Sophia 3 gives you?
True, clean, jitter-free HDMI output. But the real engineering triumph isn't just the video. Crucially, it provides HDMI with embedded SPDIF digital audio.
A single cable solution for high-fidelity video and sound.
Something modern users just take for granted, but to achieve that in a machine that was originally spitting out fuzzy analog signals, that takes professional-grade design.
You're getting into high-speed digital electronics territory here.
You really are. To get the video and audio seamlessly combined and sent over HDMI, the board uses specialized chips, specifically lattice semiconductor TMDS devices.
TMDS.
Transition minimized differential signaling. It's the protocol that HDMI uses. Those chips are basically encoding the Atari's video signal into the modern digital language an HDTV can understand.
And Simius had to give some very specific design warnings about this, right? This is where the precision engineering really comes in.
Oh, yeah. Very specific. You can't just treat these high-speed digital traces on the circuit board like normal wiring. They explicitly warned against passing the TMDS lines through via those little holes that connect layers of a PCB.
And why is that so critical for these digital signals?
Every time you send a high-speed signal through a via, you introduce a slight impedance mismatch. It's like a little bump in the road. At the frequencies needed for digital video, that bump causes signal reflections and degradation. You lose integrity.
I see.
To maintain the signal, the traces have to be designed for a precise 100-ohm differential impedance.
So the physical pathway for the digital signal has to be perfectly managed. We're talking professional PCB layout, not just, hobby tinkering.
Exactly. If that impedance isn't perfect, the signal falls apart. You get dropouts, sparkles on the screen, or the TV just won't lock on at all. This is why the SOFIA 3 is so respected. It applies modern, industrial-grade design principles.
And it doesn't exist in a vacuum. The synergy with other modern upgrades is remarkable, especially with the Pokémax 4.
The Pokémax 4 is a huge piece of this puzzle. It's an FPGA replacement for the original Poké sound chip. It offers things like quad Poké support.
So 4 separate sound channels at once.
Right. And it also has its own SPDIF digital audio output.
And these two components work together.
Perfectly. Simius provided instructions on how to physically connect the Pokémax 4's digital audio output directly to the SOFIA 3 board.
So you get a fully digital audio path.
A fully digital path. You take the enhanced multi-channel digital audio from the Pokémax, pass it digitally to the SOFIA 3, and the SOFIA 3 embeds that signal right onto the HDMI stream. You've bypassed every messy analog conversion in the Atari's history. It's pure, pristine, digital sound and video.
And this whole effort extends beyond just the computers, right? They're supporting the Atari 5200 console as well.
They are. The 5200 Super System, which shares much of the same core tech, they noted progress on the 5200 variant, which needs a slightly different board layout, and they released a new configuration file, SVU-NF2, to dial in the specific timings for the console. So yeah, the high-fidelity revolution covers the entire Atari 8-bit family.
All right, now we pivot. From physical expansion inside the machine to connecting that machine to the entire world.
This is where things get really wild.
The FujiNet peripheral has, it's fundamentally transformed the Atari 8-bit. It's turned it from a standalone box into a modern network device.
Absolutely. If SOFIA 3 solves the video problem, FujiNet solves the connectivity problem. It can emulate disk drives and printers, sure, but its real revolutionary power is its specialized network device, the N device.
Okay, let's go deep on this, it seems. Counterintuitive. How can a 1979 machine with a 1.79 millihertz CPU handle modern internet protocols? What's the magic here?
The magic is total, absolute offloading. The Atari 6502 is not only slow, it has minimal RAM and zero built-in ability to handle the heavy lifting of modern networking. Think about all the layers, TCP/IP, Wi-Fi security handshakes, DNS lookups.
6502 would just grind to a halt.
It wouldn't even know where to begin. So the FujiNet hardware is built around a modern, powerful ESP32 processor. This chip is lightning fast, has plenty of RAM, and is designed for networking.
So the FujiNet does all the work.
It does everything. It handles the TCP/IP stack, connects to Wi-Fi, resolves domain names, processes the raw internet traffic. It's an extremely smart, dedicated network card. And the crucial part is it only passes the raw, clean data stream back to the Atari 6502.
So it's like a 2025 internet interpreter for the 6502.
That's a great way to put it. The Atari just sees a stream of data coming from what it thinks is a serial device. It bridges the gap without burdening the host CPU at all.
And this requires constant updates. We saw firmware 1.5, but let's zoom in on a highly technical but critical update to the NDEV.com driver in February 2025.
This update was essential for performance, especially in dynamic applications. Historically, when the Atari wanted to know if new data had arrived, it would poll the N device. The problem was knowing how much data was waiting.
And the update changed that.
It modified the behavior of status calls. Now, a status call returns the total number of bytes waiting in a variable, and that number can go into 65,535.
A 64K buffer.
A massive buffer. Before, the Atari would have to request small chunks repeatedly, which added a ton of overhead and lag.
So why does knowing the exact buffer size matter so much?
Because it maximizes the pipeline. If the Atari can ask how much data is waiting, and the end device says 60,000 bytes, the 6502 knows it can issue one huge read command and grab it all at once.
It minimizes the back-and-forth chatter.
Exactly. It smooths the data flow, which is crucial for responsive networking. It is a fundamental shift in I/O efficiency.
And this whole ecosystem is smart enough to bridge the hardware and software worlds, right, with the FujiNet PC project.
Yes, this is huge for developers. FujiNet PC lets you connect emulators like Altera or Atari 800 to real, live FujiNet networks.
So a coder on a modern PC can test their networked app against people using real Atari hardware.
Seamlessly, it creates this amazing cross-platform testing and connectivity environment.
And the ultimate utility of all this is bypassing physical media entirely, using the nload command.
NLOD is truly transformative. It lets the Atari remotely load and run executable files directly from GitHub or web URLs like apps.irata.online.
It replaces floppy disks.
It replaces everything. No more swapping disk images, no more copying files. You boot your Atari, type a command, and instantly download and run complex software from the internet. It's a modern app loading experience on a 1979 computer.
This successful networking naturally leads to real-time interaction, not just downloading files,
It had to.
which is where the FujiNet game lobby comes in.
The lobby centralizes the whole experience. It gives structure to this new online world. Users can find chat channels and, most importantly, find and join real-time online multiplayer games.
On an Atari 800.
On an Atari 800. For a machine that predates the commercial internet by decades, this is just, it's revolutionary.
And the big proof-of-concept example from late 2025 was the introduction of Atari 5-card stud poker.
It's a simple game, but it's profoundly validating. It confirms the reality of networked Atari gaming. You can log in, choose a lobby, and play against human friends or against bots if no one's around.
Which proves the infrastructure is stable enough for the rapid data exchange needed for real-time multiplayer.
It's far more complex than a simple file transfer. It works.
And if we loop back to the hardware for a second, that potential 115.2K baud rate would massively impact this, wouldn't it?
Oh, absolutely. The speed of data exchange is everything in low latency gaming. If they can push that serial link to 115.2K just with a software tweak, the communication between the Atari and the FujiNet gets 6 times faster.
Which means faster screen redraws, more responsive control.
Less lag. It's another example of the community not just being content that it works, but being determined to make it work fast, to make it feel like a modern, responsive device.
All right, let's move from networking to pure software performance. This is where the sheer ingenuity of modern 8-bit developers just shines.
This is where they start breaking the laws of physics. The challenge is taking that 1.79 megahertz 6502 and forcing it to handle graphics and logic that were designed for 16-bit arcade boards.
And the ultimate example of this impossible port trend in late 2025 was the release of Street Fighter II for the Atari XE-XL.
The community buzz was huge. Over 680 replies in the development thread.
Why was this game so technically challenging to port?
The challenge is just gargantuan. The arcade original was a dedicated system with specialized graphics hardware. It had massive sprites, multi-layer parallax scrolling, fluid animation.
Things the Atari 8-bit was definitely not designed for.
Not even close. The Atari has limited colors, minimal memory, and relies on the GTIA chip, which is powerful for its time, but it's not a 16-bit arcade system.
So what were the technical tricks they used to replicate it?
They had to leverage 2 highly optimized systems. First, the GTIA's Player Missile Graphics System, or PM Graphics.
Right.
The GTIA lets you have a few movable objects, the players and missiles, that can be redefined on every single raster line of the screen.
Wait, on every single horizontal line of pixels being drawn, they're redefining the sprites dozens of times per screen refresh?
Every single time the electron beam hits a new line, they are constantly cycling the color registers and redefining the shape data. This creates the illusion of more detailed, multicolored sprites than the GTIA is technically supposed to support.
And the second technique?
Sophisticated bank switching. This is crucial for a game with such massive assets.
Explain bank switching for us.
The Atari 8-bit has a memory limit. Even with 128K of RAM, the 6502 can only directly see 64K at any one time. Street Fighter II has way more than 64K of animation data, backgrounds, sounds.
So bank switching is how you get around that.
It is. It involves rapidly swapping out 8K or 16K chunks of memory that the 6502 can see, instantly replacing them with a new chunk that has the next animation frame or piece of code.
So if Chun-Li throws a kick, the code swaps in the memory bank with the kick frame, displays it, and then instantly swaps into the next frame, all within a fraction of a second.
It is brutal. Cycle exact optimization. It's this combination super fast PM drawing and lightning fast bank swapping that delivers a fighting game experience. It's turning a 1.79 megahertz machine into a visual spectacle.
We're also seeing a trend of cross-platform homebrew, like Overflow Santa, released for the 8-bit computers and the 5200 console at the same time.
That trend shows how deeply developers understand the core chips. Because the 5200 is basically a simplified 8-bit computer, developers can create one code base and just adapt the I/O for each platform. It maximizes their reach.
And then there's the text adventure revival,
Yeah.
with the port of Arania.
This is a perfect example of blending old and new. It's an old ZX Spectrum game, ported using the DAD parser, and then enhanced for modern systems.
And the enhanced Atari version has raster graphics, background images.
It does, and their origin is fascinating. They were initially AI-generated images, which were then manually processed and color-reduced to fit the Atari's highly constrained display format.
Using the very newest AI tools to create art for the oldest constraints.
It's a powerful statement, isn't it? And the multi-platform release highlights the different constraints of each system. The source material mentioned, the C64 version has a 9-second load time.
Which is an eternity in 8-bit terms.
It is. And it shows the technical trade-offs. The C64 might be optimized for its sound chip, but its disk subsystem is often slower than the Atari's. Developers are constantly juggling CPU, memory, and I/O speed.
This all brings us to the ABBUC software contest, which is really the formal engine of innovation here.
The ABUC contest forces specificity and quality. And in the 2025 submissions, we see two brilliant but diametrically opposed approaches. You have the complexity of Shrinker 4 and the extreme minimalism of 1K at Taskoid.
Let's start with Shrinker 4. What was the developer's core obsession here?
The developer, Kevel Dufer, was obsessed with having a boot disk with loadable levels that did not rely on a standard DOS or disk operating system.
Why get rid of the DOS?
Because the DOS takes up precious RAM and CPU time. By ditching it, he freed up the maximum possible memory for the game itself. This was his dream, as he put it.
So how do you load levels without a DOS to manage the disk?
You have to write your own sector management and decompression routines right into the boot sector. He compressed the levels with the ZX5 algorithm, and the game loads them on the fly, managing all the sector reads internally.
He basically wrote a custom tiny OS just for this game.
That's what it is. It's peak 8-bit optimization. And on top of that, he pushed the visuals, getting 6 colors for the player sprite instead of the usual 3, and he included voice output.
Okay, now contrast that massive approach with 1K Asquith.
This is the definition of packing a universe into a teaspoon, a complete breakout clone and a minuscule 998 bytes.
You have to pause here. 998 bytes. That's less than the text in a single long tweet. How is that even possible?
It forces you to discard everything non-essential. You use procedural generation for the levels, and for graphics, you get creative. It achieves 120 on-screen colors by using the Ataski text character set.
Wait, 120 colors?
It uses text mode, not graphics mode. By cleverly redefining the text characters with different color registers, you can stack various shades and achieve a much broader perceived palette. You're using character blocks as micropixels.
And the co-op mode in that game is just a brilliant innovation born from constraint.
A masterpiece of design efficiency. Player 1 controls the bat's movement, standard stuff. But Player 2 controls the ball's booster for speed and aiming. It forces this intense, coordinated teamwork, all because programming 2 separate paddles would have taken up too much space.
And we have to give a nod to the Atari 2600 homebrew scene, with the High Score Club spotlighting champ games.
The 2600 is arguably the most constrained platform in the world, with only 128 bytes of RAM. And champ games consistently proves it can handle complex concepts. Tomahawk 777 has a lowering water level gimmick that constantly changes the playfield.
And Dino Eggs.
Dino Eggs is famous for rendering the Bigfoot graphic. Rendering any large, distinct character on the 2600 is brutal. It requires extreme cycle-by-cycle coding to assemble the image as the screen is being drawn. It's just incredible work.
So if the ABUC contest is about game design, the demoscene is about pure, uncompromising optimization.
The demoscene is where the 6502 is pushed into artistry. It's about visual spectacle over playability. Events like Silly Venture in Poland are the pinnacle.
The winners in the main demo category, Rizzo Duty and You, were running things like real-time 3D rotations and complex procedural graphics, right?
Effects that you'd think belong on a 16-bit console, all done with cycle-exact coding.
But the real The technical mindbender is the 256-byte intro category. The winner, with incels interlinked, fits a visually compelling animation and music into a mere 256 bytes.
Wait, I need to stop us there. 256 bytes. That is genuinely less memory than the basic header of almost any digital file created today. It's smaller than the file name of a modern game. How do you even begin?
It's digital sculpture under a microscope. You can't store graphics. You can't store music data. The entire program has to be a highly compressed mathematical equation.
So it's not storing the image, it's storing the formula for the image.
Exactly. When you run it, that 256 bytes expands, procedurally generating all the sound, motion, and visuals. It's the highest form of respect for the 6502 architecture.
And this obsession with optimization filters down into other challenges, right? Like the Logic or Christmas challenge to draw a snowflake.
Right. It immediately sparks a debate. Do you store the data raw? Use run-length encoding? Or, the hardest way, do you find a mathematical pattern to draw it with almost no data storage at all? It's this constant debate about efficiency versus size.
The goal is always the same. Make the 6502 do more with less.
And none of this happens in a vacuum. It requires an organized infrastructure, preservation, and media to showcase the work.
The community structure is what gives the platform its longevity, and the organizational spine of that community is, without a doubt, the ABBUC, the Atari Bitbiter User Club.
Their role as a publisher is critical. They run the contests and publish their quarterly magazine, which is now available worldwide in English.
That global reach is essential. It formalizes the knowledge base. And beyond that, they coordinate these massive preservation efforts.
Right, the 8-bit software preservation effort hit a major milestone. But it's not just about archiving games.
No, the recovery of rare documents and professional software is just as important. The Antic podcast had a great episode on this, Steampunk Atari.
What did they cover?
Two things. First, the recovery of a professional air navigation RNAV software package, complete with the manual and the source code. This was a serious commercial tool.
And the second thing?
The scanning of historical newsletters from the Jersey Atari Computer Group from the mid-'80s.
Why are those old local newsletters so important to a modern engineer?
Because they document the things that never made it into national magazines. Local hardware hacks, unique programming tricks. They detail the everyday ingenuity of users. It fills in the social and technical history of the platform.
And we can't ignore the corporate side of this. Atari SA's focus on retro creates a halo effect for the homebrew scene.
It does. And the Atari 400 Mini is the direct corporate link to the 8-bit computers. The late 2025 updates show they're serious about improving the emulation.
What were the most important fixes?
Accuracy and control. There was a graphics fix for MULE, which is a classic, and critically, they corrected the 5200 analog mapping.
Making it true analog, not digital.
Exactly. Which is essential for playing games like Star Raiders faithfully. It drastically improves gameplay accuracy.
And they added features for the homebrew community, too.
The display height configuration, that's a big deal. Many advanced homebrew games use the overscan areas of the screen. This feature makes the commercial Mini compatible with the community's bleeding-edge releases.
And before we wrap up, we have to mention the news about zero-page homebrew. There was a scare they were shutting down.
A huge moment of panic in the community. ZPH is a vital promotional engine, and they run the Homebrew Awards.
But they're back.
They are back. They confirmed they'll be returning in January, and the 8th annual Atari Homebrew Awards are back on track for February. A huge relief for everyone.
So we've covered the whole landscape. Hardware resurrection with the 1090 XL, digital video with Sophia 3, the network reality of FujiNet, and the extreme optimization of the demoscene. The key takeaway isn't just that the Atari 8-bit is alive. It's thriving because of this sophisticated, technically driven innovation that's often surpassing the machine's original capabilities.
Which raises an important question. We're seeing these machines do things today, high-speed networking, real-time 3D, that were considered impossible or at least commercially unviable 40 years ago.
Developers are solving problems the original engineers had to just bypass.
Exactly.
So what does this all mean for you, the learner? The machine isn't a relic to be maintained anymore. It's a specialized, high-performance platform that demands new, advanced skills. The fact that modern developers are fixing timing issues with glue logic and completing alpha-level firmware is proof the platform is being actively developed as a high-end system.
It's a remarkable phenomenon. Today's 8-bit engineers are effectively completing the original Atari mission. They're making the 1980s vision of the infinitely expandable home computer a reality for the very first time.
Which brings us to our final provocative thought for you. The original engineers of the Atari 800, people like Joe Duckworth, had to make technical compromises for cost and for deadline.
They did.
Given that today's developers are conquering those very compromises, timing, networking, graphics, are the constraints of retro computing actually serving as the ultimate proving ground for creative engineering? Are the challenges left behind by the 1980s team finally being solved in the 2020s, maybe with more ingenuity than was ever originally intended?
Think on that until our next deep dive.